stealth technology, the internet, GPS in the palm of your hand, autonomous operation.
Technology is a driver of our times. Since its founding in 1958 in the midst of the Cold War, DARPA, the Defense Advanced Research Projects Agency, has been a driver of technology. Welcome to Voices from DARPA, a window on the people behind DARPA's signature mission to redefine what's possible. My name is Ivan Amato, and I'm your DARPA host. Today's podcast will be a little different from most of the others. You'll hear the voices of program managers as you usually do, but this episode will feature the synergistic efforts of several programs that are opening a pathway to what I am calling Science 2.0. I am referring here to a turbocharged scientific enterprise that could accelerate the pace of scientific discovery and the development of technologies, knowledge and evidence-based decision-making and policy-making, and other capabilities based on this new knowledge. Perhaps Hiroaki Kitano, director of Sony Computer Sciences Laboratories, articulated this notion most clearly and boldly. He suggested the research community should take on a grand challenge to develop artificial intelligence systems that by 2050 will be making Nobel-caliber scientific discoveries. Science has been the primary engine of civilization's advance, Kitano says. So AI tools that can accelerate scientific discovery in general could exert enormous leverage on many fronts important to society. I anticipate in the future, Kitano wrote in 2016 to give a flavor of what he has in mind, AI systems that will make a succession of discoveries that have immediate medical implications, saving millions of lives and totally changing the fate of the human race. Just a note before proceeding, I recorded conversations with DARPA program managers Joshua Elliott, Jiangying Zhou, and Bartlett Russell from our respective homes so we all could do our parts to slow the spread of COVID-19. That's why you may hear some ambient household sounds like trucks and birds, even cicadas. I want to start with Joshua Elliott, a program manager since 2017 in the agency's Information Innovation Office, which has a long history in AI research. Joshua credits researchers' evolving reliance on powerful computational tools and the creation and analysis of vast databases with accelerating the pace of scientific discovery. He says this human-machine alliance has gotten us closer to a vision of an early and now famous DARPA program manager, J.C.R. Licklider, who is credited with formulating in the 1960s a lasting and guiding vision for how computers and human beings can become teammates in the quest for knowledge and to become more powerful and capable actors in the world.
I guess I would argue that human-machine symbiosis in science, that has been the primary driver, is how do we enable scientists through computation, through big data, through all these things to actually discover more and bigger things faster. Of course, we've already seen human-machine symbiosis dramatically improve and accelerate science over the last 50 years. But I think there's still a lot more to go, and that with the modern generation of AI, I think that we can really take that to the next level of the sort of the Licklider concept of human and machine symbiosis.
Joshua's program manager colleague, Jiangying Zhou of the agency's Defense Sciences Office, is doing what she can to hasten the day when these symbioses typify the way science is done. Consider her Artificial Intelligence Research Associate Program, or ARA for short. We are talking here of developing an AI, an artificial intelligence, that is competent enough to serve as a genuine scientific collaborator with a human scientist. Such human-machine teaming would be a cornerstone of the Science 2.0 era. When I asked JZ, as Jiangying Zhou is most often known by her colleagues, about that, I liked the way she put it.
Is it possible for us to develop AI technologies that could, by analyzing scientific data, to figure out the fundamental governing laws of the nature? So an example is, so everybody probably remember that Newton, by sitting down under the tree watching the apple falling on the ground, he eventually figured out the law of gravity. And so the question is that, is it possible for the AI technologies to be developed to the point that could also have this level of abstraction capabilities? So the ERA program basically is set up this vision to ask what are the fundamental components that are needed for the AI technologies to achieve this kind of scientific discoveries.
But Jay-Z, like Sony researcher Hiroaki Kitano, is not just talking about artificial intelligence that just recapitulates previous discoveries by scientifically inclined human beings.
This researcher from Japan, Kitano, so he asked these questions that can the AI technologies be developed such that it has the quality, the same caliber of a human scientist that can make scientific discoveries worthy of Nobel Prize, right? So that we are talking about new discoveries and new insights, new laws of nature.
For her part in spurring the research community to develop AI tools that might perform like artificial scientists as skilled as the best human scientists, Jay-Z's ERA program has two primary objectives. One is to make machine learning, a current mainstay of AI underlying such things as speech and image recognition, capable of discerning patterns in data without relying on human beings providing training sets of data. This is essentially like showing a child a bunch of individual pictures of, say, a chicken, and then telling the computer to then go out and look at every animal picture on the internet and label the ones that are of chickens.
But in the realm of scientific discovery, you typically do not have this kind of training examples to teach the AI system to uncover the patterns. So the question is that can we develop AI technologies so that it can explore the unknowns on its own and be able to abstract the principles that underlie the data and the patterns? The second, and I think it's a harder challenge that ERA is trying to address, is for the AI system to know when it does not know.
This could not be more important. Human scientists are always weighing their measurements and observations, their data, in the context of hypotheses. One of the perils is that the same data sets can correlate consistently with multiple hypotheses or mathematical statements that can look like laws of nature and yet are wrong, have no foundation in reality, or are even absurd. It can happen to the best of them. When Copernicus first argued in the 16th century that it was the Earth that was circling the sun and not the other way around, he managed to preserve a factually false feature of the then accepted Ptolemaic Earth-centric system that had the planets following perfectly circular orbits as specified by Aristotelian astronomy. This led to a defense of oddly complicated planetary motions in which planets sometimes took off in small, perfectly circular epicycles along their overall orbits to account for the actual observations of planets appearing in the sky to sometimes backtrack. Let's hear Jay-Z explain how an AI scientist most likely would fail to see in the astronomical data before its digital eyes the elliptical pathways that Johannes Kepler was able to discern in the early 17th century.
We actually had a demonstration of this tendency for the AIs to try to explain unknown phenomena with explanations that are perfectly able to explain the observations at hand, but it's incorrect. So, for example, that I mentioned in the ERA program, one of the examples that making scientific discovery is to discover the law of planet motion, the Kepler's law. And now one of the performers actually ran experiments. They took a set of perfect data, planet observation data, and add noise to the data, a little bit noise, and run the AI system and ask the AI system to find equations. And because of the noise, the AI system discovered very complex equations that have nothing to do with the laws of the planet movement, but it actually is a better fit than the original.
I mean, given the data plus the noise, it made sense of that artificial data set.
Exactly.
Helping AI scientists to not make such errors by deriving mathematically sound models that fit the data beautifully while being factually meaningless, irrelevant, or worse, misleading, weighs heavily on the mind of Joshua Elliott. His program, known as ASCII, which is short for Automatic Scientific Knowledge Extraction, is about trying to assure that the models scientists devise about how the world works, or that managers and commanders rely on for making decisions, actually reside on sound, causally backed foundations, or in short, that the foundations for claiming knowledge and taking actions make sense.
The goal of ASCII is really to dig into these black box models that scientists use to operationalize their knowledge and that get leveraged for decision support, and to develop tools that enable us to actually do what I call machine-assisted curation and modeling and machine-assisted insight. So being able to both extract and assimilate knowledge into models, curate those models with AI assistance, and then also being able to extract insight from those models in rigorous ways using various AI approaches.
Within the DARPA and DoD contexts, Joshua is hoping to improve decision-making, a process based on experience as well as on theories about how people behave and how conflicts unfold. But right now, he can't help but imagine how his programs could deliver near-term capabilities to help accelerate solutions to even the most present global-scale threat, the COVID-19 pandemic.
And really, there's never been a more obvious and clear need for technologies like this. In the biochemical sort of human and viral biology area, you have tens of thousands of publications that are relevant, with hundreds and maybe now up close to thousands, if you count preprints, of new publications with new information that's relevant to the story coming out every single day. And it's just impossible for folks to keep up with that. In the case of COVID-19, you're trying to extract causal associations between proteins and between genes and between small molecules that may be drug candidates, for instance, and how those things interact at the biochemical, mechanical, mechanistic level so that you can compile that extracted knowledge or model fragments in some sense. Each of those fragments is sort of a model in itself, and you want to be able to compile that over, tens, hundreds of thousands of documents, millions potentially of pieces of knowledge fragments, compile that into a large-scale model that you can actually start doing complex forward simulation and inference over.
In some ways, Joshua is saying, it's the sheer size of the scientific enterprise and its current productivity that can be a drag on scientific discovery. In something like the complex ways viruses infect cells and cause pandemics, there just are too many scientific pixels for any one human mind to assimilate and assemble on its own, without the assistance of something like AI assistance that Joshua is asking the researchers working on some of his programs to develop.
You may have this entire complex cell signaling pathway that actually answers broad questions about these complex diseases, but it might be spread out, the information from it might be spread out over thousands of publications, and you need to extract each of these pieces of knowledge and piece them together in order to tell the whole story. So that's a big part of it. The other part of it is trying to extract actually experimental tests where these results have been validated as observations. That provides you with the kind of knowledge that you can use to actually validate your model against the real world.
Another one of Joshua's programs, Data-Driven Discovery of Models, or D3M, is focusing on another signature feature of contemporary science, the generation and analysis of huge databases ranging from genomic sequences of thousands of species to the social media behavior of millions of people. Joshua thinks data science can be leveraged way more to accelerate science across many problem areas.
The biggest problem with data science has always been sort of the democratization of it. It's something that, despite a lot of people's preconceptions, actually requires quite a lot of both mathematical and just engineering sort of expertise. And a lot of that is not sort of the advanced math. A lot of it is the kind of nitty-gritty stuff that you don't often think of, like data cleaning and normalization and feature engineering and some of this stuff that's just working with data is very hard. And so D3M is all about machine learning for everyone, data science for everyone, making these advanced methods of data science that have evolved over the last several years especially, making them accessible to a non-data scientist, and ideally even making them accessible to a domain scientist who might have a different kind of expertise that they could actually apply to further improve data science. I mean, for example, to discover the best possible features for a model often requires domain expertise. But domain experts are often limited in their ability to use that by the fact that they're not data scientists and they can't afford to hire a data scientist at $120K a year or whatever they're going at now. And so the tools we're developing in D3M, they broadly go into the category of auto machine learning and also intuitive interfaces for actually non-specialists, non-data scientists to be able to engage with the modern tools of auto machine learning, intuitive and really broad ways, with problems ranging from traditional tabular regression problems to image classification to NLP problems, natural language processing, and to graph problems.
By tabular regression, Joshua is referring to the seminal scientific challenge in making sense of how two different things in the world relate to each other. Increase the temperature of a contained gas, for example, and its pressure increases in a mathematically lawful way. By graph problems, networked phenomena, whether it's a city's communications system or a commander's warfighters and assets, Joshua is referring to phenomena that can be represented in graphical formats. Another program manager in the Defense Sciences Office, Bartlett Russell, who is known as BART for short, is also a champion of accelerating science by empowering practitioners with AI tools that lend them expertise they might not otherwise have.
My general philosophy towards accelerating science, accelerating capability, it comes down to enabling the human in general. No matter how you cut it, the human brain is still the most sophisticated computational system on the planet, right? And so for all of the advances in AI that we have, while there's incredible work going on in that area, my view and all of the work that I'm driving on here at DARPA is about using those tools to enable the human brain, to enable the human thinker, to allow that person to do more with less.
She is hoping that one set of tools to enable scientists to eke more discovery out of their research will emerge from a program that one of her colleagues in the Defense Sciences Office, Office Deputy Director Phil Root, is running. It's called SCORE, short for Systematizing Confidence in Open Research and Evidence. And it could spare scientists some of the increasing burden of keeping up with the raging torrent of good, but also not so good scientific papers that might or might not be relevant to the scientific questions a particular scientist cares about.
What SCORE is trying to do is help cut through all that uncertainty by assigning essentially a confidence score or a quality score to different studies, and is asking the question, can you predict ahead of time when, based on the way the study is put together, based on the methods that the researchers have decided to use, can you figure out which ones are likely to replicate after the fact? The idea is if we can raise standards, and we can have a lot more confidence in the studies that come out on the other end. And that way we can know if a study about red wine tells us it's good for our heart, is actually good for our heart, or it's more likely to be good for our heart, or if it really is something we have to worry about when another study says it's not. So that, I think, really does speak to one of the underlying principles of science in general, in that we require science to be reliable. We need it to be reliable in order to build things from it. One of the goals of SCORE is, can you better filter out the really reliable, the very good, from the maybe throwaway study that somebody did to get a publication, but is really not that great. I think that in itself would greatly advance the speed of innovation. When doing a literature review, you don't have to go through hundreds of articles. You can go right to the 10 or 12 that you know are particularly reliable.
Joshua Elliott envisions applying similar AI tools, but to retroactively clean up the scientific literature so that investigators can feel more confident that the evidence our scientific understanding and decision-making protocols are based on is sound and is not instead equivalent to a house of cards.
How do we take machine technology in order to be able to reverse, first of all, a lot of those negative consequences, go back through the literature for the last 20 decades and try to discover papers and findings and things that are in fact not reproducible, or perhaps even completely wrong, or perhaps even fraudulent? How do we go back and find errors in models, computational models that have been used to support, multi-billion-dollar decisions that have been used to support literally life and death decisions within the DoD? These models are black boxes that are often poorly understood even by the people who are using them. And that needs to be untangled. And that's one of the biggest goals of ASCII is to try and really untangle that sort of mess that we've gotten into.
Bart Russell, who has a cognitive science background and a strong interest in furthering the reliability of social science, also takes the idea of democratizing the practice of science that Joshua spoke about in another direction, in her case to open science, and data science in particular, to non-traditional practitioners. The hypothesis here is that the more minds that are applying themselves to science, the more scientific discovery we can expect.
All of the things that I'm looking at tackling while I'm here at DARPA really focus on leveraging new AI tools to enable human ingenuity, rather than take the view that we should write the human out of the loop, for instance. My thought is, if we empower the human to understand enough about those tools, and I don't mean just highly trained humans, I mean the every human, the every person, then I think we can unlock this base of ingenuity that we have in this country in particular, in a way that we haven't yet, that could provide pretty profound advantages for our economy as well as for our defense capabilities. One of the very focused efforts I'm looking at here really is about loosely calling it human factors in the age of AI and autonomy. How do we make complex AI tools accessible to non-data scientists, not just so they can use them, but so they can innovate with them? And that's an important distinction, because using them means you use them for the purpose they were designed to be used in. Innovation means that you can use those tools in ways that nobody has thought of before. And this is where citizen science can be extremely powerful. So again, rather than writing the humans out of the loop and putting in enough safeguards so they can never use that system in an off-nominal situation, I take the view that AI should be instead transparent enough that you don't need to be a data scientist in order to figure out how it's been engineered, but you can understand enough about its capabilities and limitations in those capabilities that you can make calculated risk decisions about how and when you can use it in new ways. So if we can make these AI tools more accessible to the every person, regardless of their training, it greatly increases the number of people that we can dedicate to more problems, right? Because as it is, I'm now taking a data scientist and attaching them to every team. Wouldn't it be cool if those data scientists could then focus instead on pushing the edges of AI rather than helping me with my cognitive science problem? That's one way. That has to do with the actual discovery of capabilities in the first place. The other way is about, again, this off-nominal use of the same tool. Can you increase the utility of a tool you create wildly because, again, the every person knows how to use it well enough they can innovate with it.
Much like Joshua Elliott, Jay-Z sees AI assistance accelerating science by digesting far more of the available scientific findings out there as a means of automatically generating hypotheses that their human scientist partners could then vet for potential further pursuit.
There's a huge number of publications, so really it's hard for individual scientists to keep up and to make sure that they understand all the latest, the greatest discoveries to help their own research. But imagine with the AI scientists that are able to digest all those publications very quickly, very efficiently, and to be able to at least provide hypotheses and possible principles to from those discoveries and work with the human scientists to validate. And I think that's that's actually a completely different way of doing science as we are doing now. In the Science 1.0, AI technologies are mostly functioning as tools, and they are directed and used by scientists. They are not teammates. Actually, one of the visions of the DARPA's AI next campaign is to enable AI to turning from tools to teammates.
By AI Next, Jay-Z is referring to a large portfolio of programs and other efforts that DARPA is running to improve AI on many fronts. In the context of the coming era of Science 2.0, she would like to see a new amped-up collaboration of human scientists with AI teammates to help crack notoriously difficult and complex scientific and engineering problems. Among these is the challenge of fully understanding phenomena like turbulent flows associated with, for example, supersonic flight. Another is the huge challenge of discovering and designing new and more capable materials, which in turn lead to new and more capable technologies made of those materials.
The design space for the new material, is extremely complex. So the DoD domains, for example, what they are interested in is that whether there's a capabilities for the AI technologies, so that if I state that I want this specific properties in the materials, the reverse engineering, designing the right materials that can satisfy these material properties. And given the possibilities of, the material properties are governed from the very low level, by the atomic level, by the atoms interactions, and then at the high levels by their topologies and geometries. It's extremely complex space. So to find the right designs to satisfy your material properties, actually extremely complex problem, and so that's another area of domains that the AI technologies that we're hoping that will be able to help to accelerate this material discovery process.
Jay-Z says a few ways AI tools could help pull off this kind of acceleration in research is by making otherwise unwieldy simulations far more efficient, and by reducing the number of actual experiments and observations scientists need to make to answer their questions.
We are trying to see that whether AI technologies can reduce our reliance on making huge number of measurements or observations. So that will have a huge implications in terms of the cost and the ability to adequately model the phenomena. AI technologies can help to make this simulations more efficient, and to be able to manage, for example, the interactions between multiple different scales more computationally efficient, so that we can explore more design space.
Joshua Elliott concurs, and he says that's where another one of his programs comes in. If some part of the scientific process can be automated, he thinks it ought to be.
Yeah, so SD2, which is synergistic discovery and design, is all about really trying to, once again, to apply automation to eliminate those bottlenecks and biases and problems throughout the experimental cycle, from design, building, testing, analyzing, and then back to designing again experiments. And it's focused on some of the most complex experimental domains you can imagine. So synthetic biology, both in traditional and in novel organisms, perovskite's chemistry, which is a thin film chemistry that looks very promising for the next generation of solar cells, and also protein design and folding. These massively complex, computationally intensive, infinite dimensional design spaces. And how can we create the tools, create the protocols and the infrastructure, both the data infrastructure and the computational infrastructure and the experimental infrastructure, to be able to automate the key parts of that process. Not automating the full process, that's still quite a ways away, although, not a terrible fantasy to have. But automating the key aspects that can be automated, either to increase reproducibility. For example, there's technologies being created for lab software and protocols, so that an experimental protocol performed in one lab can be ported over and reapplied in another lab rigorously without any ambiguities of interpretation, so that a scientist can actually publish their experimental protocol explicitly along with a scientific publication.
Part of the challenge to developing AI scientist teammates resides in the way scientific experimentation and its results, the data, are communicated and codified. Joshua, who wants not only to accelerate scientific discovery, but also to develop new means for being confident about making decisions, explains.
Over the last 5 decades, scientists in many fields have been encoding much of their knowledge into these computational models with often poor documentation and opaque assumptions. And so we can't just start afresh and say, from now on, you have to follow this good set of standards. We actually have to figure out ways of extracting and organizing and presenting and making that knowledge available. And that's really where the AI comes in the case of ASCII and our sort of Science 2.0 goals there. In order to use the outcomes of this Science 2.0 to actually be able to support Decision-Making 2.0, which is a big part of my objectives, we really need to rethink the way that we encode, apply, and communicate the outcomes of our science. Right now, for the most part, it's encoded as, these large, complex, opaque, black box computational models that some expert says, trust me, this model is reality and that's it. And it's communicated as a set of numbers with very little context, with very little accounting for what were the assumptions and parameterizations and things that went in to produce those. And that's just not acceptable in a time like this, in a time where things are changing very, very rapidly, where the best possible information in science is needed, and where you actually have to understand what the model is telling you.
Joshua says we have a long way to go before we have artificial scientists and research collaborators of the sort that Kitano and the early DARPA visionary J.C.R. Licklider challenged researchers to develop. But he says there likely will be great payoffs from the process of getting there.
In the 15 years or 50 years or 5,000 years until we get to that point where artificial intelligence is actually doing the Nobel Prize-winning science, augmented intelligence by human and machine symbiosis might actually make that period, some of the most exciting and the most creative and the most productive in human history.
Jay-Z concurs in her own way.
The pace of scientific discovery and technology development has been actually increasing. I think for a not small part actually attributing to tools and the technologies that we have, including AI technologies. And so if, for example, the AI technologies could truly actually becoming scientists, digital scientists, standing shoulder to shoulder with the human scientists, we essentially you can see a huge force multiplier.
Bart Russell muses that artificial scientists will help us solve the kinds of problems for which we always have wanted and needed solutions, including even social science questions that so far have been beyond our ability to understand and predict.
So what does it mean if AI ends up being what we hope it is going to be and not what we fear it could be? And if humans really understand it well enough to work with it? I think that, like so many technologies that we've used in the past, we'll probably use it to solve the same problems we've just had a very hard time solving in the past. The beauty of it is, so things like hunger and efficiencies, we were always looking for efficiencies. I think we'll probably apply it to the same problems. I think the most exciting part, though, are the emergent properties that none of us can probably anticipate. Looking at, again, social media as an example with Twitter, who knew that a platform that just is asking, what are you doing right now? And limited drastically how people could answer that question in terms of length, could result in nations dealing with each other in different ways. I don't think anybody would have anticipated that. The speed and the access by which we have with each other now is very different. And I anticipate that the most profound things will be ones that we cannot predict and we do not have the imagination to see yet.
One mind-blowing possibility that Jay-Z points out is that artificial intelligence, as the first other kind of intelligence on the planet applied to scientific investigation and discovery, could open up entirely new scientific vistas and styles of explanation that will take some doing for humans to even understand.
Potentially, is that the AIs might be come up explanations or descriptions of the world that's different from how we see it, and that in one way could expand our knowledge, our understanding of the universe, of the nature, and also probably means is that we humans, maybe one day we have a single tool to learn from AI systems.
It is no surprise that the pathway to AI systems capable of Nobel-caliber scientific discovery is likely to be a long one. Along the way, researchers at DARPA and elsewhere say we will need to make it a priority that any artificial scientist in a coming era of Science 2.0 does not feature the same kinds of biases, foibles, and penchants for fooling themselves that always have been part of the utterly human Science 1.0. Thanks, listeners, for sharing this time with me and some of the program managers at DARPA who are aiming to reconstruct the scientific enterprise. I hope you join us again for the next Voices from DARPA. For more information about DARPA's entire portfolio of more than 250 technology development programs, visit darpa.mil. And for links that enable you to download this podcast, go to the Voices from DARPA page on DARPA's website.